Today we are going to discussing about the module 3 of control system, time domain analysis and root stability criteria. So first we shall discuss the definition of time response and transient response and steady state response. So time response, it is the response of the system which is a function of time, which is called as time response of control system. So if any response of any system which is varies with respect to time. The second terminology, that is transient response. So this transient response, which is defined as the variation of output during the time it takes to achieve its final value. So to settle down the complete response with respect to time, which is called a transient response. So the transient response, which is symbolically represented as Ct of t. So Ct of t denotes the representation of transient response. So the next terminology is steady state response. So the difference between desired output and actual output of a system is called a steady state response. So the plot which shows the transient response and one more is steady state response. So for this response curve, we are marking here transient response. CSS stands for steady state response with respect to time. And this plot which indicate a step response curve of second order system. So Ct of t means transient response. So ESS stands for steady state, and total time is considered from 0 to settling time. So to knowing this basic concept, we shall discuss some of the input for the steady state errors. So those inputs which are given by the first type of input is step input. So this step input which is considered for position function. So the second type of input is ramp input, and the third type of input is parabolic. So for the step input, it is a constant input with respect to time t. So this A is called as constant, step input constant. So which is represented in mathematical form, that is R of t equal to A if t is greater than or equal to 0. So 0 means for all positive value of t, the magnitude is constant. So for negative value of t, this magnitude is 0. That is R of t equal to 0 for t less than 0. And the second type of input is ramp input. This ramp input gives a function velocity error constant. So it is a constant rate of change of input. So the plot shows R of t is the ramp which is input with respect to time t. This straight line slope which indicate a constant input with respect to time. So therefore, mathematically the ramp input can be represented as R of t equal to A into t for t greater than 0, 0 for t less than 0. So and the third type of input is parabolic. So here figure shows the parabolic input. So this parabolic input which is changes with respect to time t. So in this parabolic input, it can be represented mathematically R of t equal to A by 2 into t square for t greater than 0, 0 for t less than 0. So next shall move on to the steady state errors. The error which is occurs during the constant time period, which is called steady state error. This steady state error, which is represented mathematically, ESS is equal to limits t tends to infinity E of t. So E of t is nothing but an error signal with respect to time t. So if you apply the Laplace for this steady state error, so we'll get the equation ESS equal to limits. So S tends to 0, S into E of S. So here the time domain will be converted into S domain functions. So in general, the steady state error is given by limits S tends to 0, S R of S divided by 1 plus G of S into H of S. This R of S divided by 1 plus G of S into H of S, which is called a closed loop transfer functions. So for the same steady state error can be applied for the different kind of inputs. So if you apply the steady state error for the first type of input, that is positional error constant. So in general, for positional error constants, the steady state error can be given by ESS equal to A divided by 1 plus Kp, where Kp is nothing but positional error constant or positional error coefficient. So Kp is given by limits S tends to 0, G of S into H of S. So similarly, for other two inputs, for acceleration in error constant, the steady state error, which is given by A divided by K into A, where K suffix A is called acceleration error constant. So K equal to limits S tends to 0, S square G of S into H of S. So this table denotes the for all the three inputs the corresponding steady state error equation. If Kp is nothing but positional error constant, steady state error is given by A divided by 1 plus Kp. For velocity error constant, the steady state error, which is given by A divided by K suffix B. For acceleration error constant, the steady state error, which is given by A divided by K into A. So let us discuss the next concept, that is transfer function for closed loop system. So here we will consider the general transfer function for second order system. So that can be given by C of S divided by R of S, which is equal to transfer function omega n square divided by S square plus 2 zeta omega ns plus omega n square. This denominator from denominator polynomial. So by looking at the order of S, if it is S square, then we can call it as it is second order. If it is S to the power of 1, then we can call it as it is a first order system. So this from the denominator we can calculate some of the constants, that is zeta value, that is nothing but damping factor, and one more constant, that is omega n. So where omega n is nothing but natural frequency. So based on this second order equation, the damping factors having the three different conditions. If damping factor is greater than 1, the system is called underdamped condition. So if damping factor zeta is equal to 1, the system is critically damped. If zeta is less than 1, the system is overdamped conditions. So these three are the different cases for corresponding damping factor. So let us see the step response curve for the standard second order system. Here from the plot, we have to observe it C of t in y-axis, which is called total response. T is denotes the time in seconds. So this is the step response curve, which is settled at the certain time period. So from this curve, we are describing different terminologies. So those terminologies are: first is delay time, rise time, peak time, and the fourth one is settle time, and the fifth one is maximum peak occurred. So the first terminology, let us discuss the first terminology, that is delay time. So delay time, it is defined as the time required for the response to reach 50% of final value in the first attempt. So from the graph, if you are observing this graph, this is the 0, that is the starting point, and this is the 50% of time period. So from 0 to 50% time, so we'll get the delay time period. This delay time, which is given by a standard equation, that is Td equal to 1 plus 0.7 zeta divided by omega n. So where zeta is nothing but damping factor and omega n is nothing but natural frequency. Then now we shall move on to the next terminology, that is rise time. So it is defined as the time required for response to rise from 10 to 90% of final value for overdamped system and 0 to 100% of final value for underdamped system. So from the graph, in general, so the time will start from 10% and reach to 90%. From 10 to 90% time period, we can call it as a rise time. So from the graph, you have to observe it. The rise time will start from 10% and ends with 90%. This rise time, which is given by an equation TR, which represent an rise time. So TR equal to pi minus theta divided by omega d, where omega d is nothing but in a damping frequency in radians per seconds. So theta is the angle in radian and pi is the constant. Now we shall discuss the third terminology, which is used in the second order, that is peak time. It is the time, it is defined as it is the time required for the response to reach its peak value, which is called a peak time. So by look at the graph, the peak time, which is marked in the graph from 0 to maximum time period. So the curve will start from 0 and reaches its maximum point, which is called a peak time. So the peak time, which is given by Tp. So in general, the mathematical equation for peak time equal to Tp equal to pi divided by omega d. So pi, where omega d can be rewrite as omega n under root 1 minus zeta square. The next is peak occurred. The fourth terminology which are used in the time response of second order is peak overshoot. It is the largest error between the reference input and output during the transient period. Maximum peak overshoot, which is given by e to the power pi e to the power of minus pi zeta divided by root of 1 minus zeta